Okay, so we looked at the difference between standard delta G and non-standard delta G conceptually with our H2 plus Cl2 goes to HCl reaction. Now we're going to look at the mathematical arguments of how delta G shifts. Okay, now I'm not going to proceed with any true calculations here, though you will work calculations. I just want to kind of really think about this equation, the mathematical relationship between them. Okay, so we know this. If a reaction is not under standard state conditions, we have a delta G without the little circle. Okay. And we have ways of obtaining the delta G with this circle, but we have a way of relating between those two. But when you look at a reaction and you're looking at what's in there, you need to consider the conditions it's in right now to decide whether it's going to proceed spontaneously towards products or spontaneously towards reactants. Which way will it proceed? In the forward direction spontaneously or the reverse reaction spontaneously? You need to know its conditions right now. The standard delta G will say this is what it will do if everything's under standard state conditions, but very often it's not. Okay? So this is the equation that gets you the non-standard delta G from its standard delta G. So we've got our different terms in here, and that's an equation that you're going to need to commit to memory. All right? The R we're going to need to use is the one that has energy units that are useful for us. We use this joule per mole Kelvin, and really you're going to want to work with kilojoules, so you could convert this over to kilojoules per mole Kelvin, but we provide that unit, that value of R on your periodic table when you take our exam. Temperature, of course, will need to be in kelvins because our R has got that Kelvin in there, so we have that. And the Q is our reaction quotient. So we learned about reaction quotient when we were dealing with equilibrium. It's products over reactants raised to the power of their coefficients, but not their equilibrium values necessarily. It's where it is right now. So that would be products over reactants in its state. And once you know during this state what those conditions are, you can plug it in, get a Q value, and this term will change the standard delta G to a non-standard delta G. So delta G equals, you start with, here it is in its standard state conditions, and you're going to add a term, RT natural log of Q. Now, this term might be positive and make delta G bigger than this. It might be negative and make delta G smaller than this. It all depends upon the reaction quotient, okay? And we know the reaction quotient, Q, is products over reactants raised to the power of their coefficients. So I'll call the, just some coefficient, I'll call this Q and this T. I don't know. There's some power of their coefficients that it's raised to. So if you go in and you dump a whole bunch of reactants in, Le Chatelier's principle says it should go to the right. Well, did you dump enough in to push it to the right? It depends. How big is your Q? Did you put a whole bunch of products in, reactants in, making this term small and it'll shift enough? It just depends. If you want to force a reaction this way, Le Chatelier's principle says dump a bunch of products in and it'll go that way. All right, that's affecting this Q. Making it spontaneously go that way means we need a positive delta G. Did you make it big enough to do that? So we're going to walk through everything I just said slowly and stepwise and think about it bit by bit. Okay, so how does concentration affect this delta G? This doesn't change. This is a snapshot in time when everything's 1 molar or 1 atmosphere. But how does concentration, this part, affect that? Okay, we have that. Q is products over reactants raised to the power of its coefficients, and it is not necessarily at equilibrium. Now let's think about a Q that's less than 1, okay? If Q is less than 1, what do we have? We have a lot of reactants, not very many products, okay? That would give you a Q less than 1. That would be a fraction. Okay, Q less than 1, it's a fraction. What's the natural log of a fraction? What is the sign of the natural log of a fraction? Well, if you don't know, pick up a calculator and take the natural log of 1/2. Take the natural log of 1/3. Take the natural log of 1/4. What kind of sign do you get for that? Well, let me just, oops, sorry, back up the bus. So what is the sign? It's negative, okay? So if Q is less than 1, it's a fraction, then the negative log is negative, right? So you're taking this and, because this is positive and this is positive and then this becomes negative, you are subtracting away from that. Okay, what if the other is true? What if Q is greater than 1? Okay, we'll use a different color pen for that argument. If Q up here is greater than 1, what is the natural log of Q? Well, if you don't know that, get your calculator out and take the natural log of 2, take the natural log of 4, take the natural log of 100. What do you always get? It's always positive. So when you take products over reactants, if it's greater than 1, that means you got a lot of products, not much reactants. Okay, you have the natural log, and what you're going to do is you're going to be adding to this value, and the delta G is going to go up and get bigger and bigger. Okay, that's the effect that the reaction quotient will have on this term, and consequently the effect that this will have on its delta G value. So let's say that this is negative. Let's have a scenario where the delta G standard, and I'm going to rewrite this reaction so I can easily write under it. Let's have a scenario where I go to the tables and I determine that the standard delta G is a negative number. I know that that means it's spontaneous in the forward direction if everything started out, products and reactants were all 1. Consequently, if this is 1 and this is 1, then the Q is 1 and the natural log of 1 is, put it in your calculator, it's always 0. So that term goes away. But let's say it's negative, okay? Let's see what the next thing is. What does that mean? I just told you the reaction is spontaneous if it were starting out at standard state conditions. What conditions, what would Q have to do to make this reaction no longer spontaneous? I didn't say what that was. That says make delta G positive. Well, if delta G is positive, that means it's no longer spontaneous. Well, if this is negative, what must this be in order for this to become positive? Well, this has to be positive, and it needs to be more positive than this is negative. Okay, now how do we have a positive value? Okay, so if delta G is negative, what conditions of Q will make this positive? In other words, make the reaction no longer spontaneous. Well, this term has got to become positive. How does this term become positive? This term becomes positive when Q is greater than 1. How does Q get greater than 1? You have a lot more products than you have reactants. So if you dump a bunch of products in, you can take a reaction that was running spontaneously this way under standard state conditions. If you dump enough products in, you'll get this term to be big enough so that this whole thing will be bigger than that and it'll become spontaneous. What did Le Chatelier's principle tell us? If you put in a bunch of products, it can shift the reaction in that direction. Okay? So the answer to our question is if Q is greater than 1, okay, then the natural log of Q is going to be positive, and eventually this is going to be big enough in order to do that, and that happens when you have way more products than you have reactants. Now, this is not telling you how much more products. It might be 4 billion times more products than reactants before it gets big enough to overtake that and become positive, but there's going to be a point where you've got so much products, you are going to make the reverse reaction spontaneous. Let's walk through the same logic but in the opposite scenario, okay? Let's imagine a situation where, let me find something to erase with, bear with me here. Okay, Now I have a scenario where I have got the delta G, and its standard delta G is positive. Okay? So it's positive. In other words, if you're under standard state conditions, the reverse reaction is spontaneous. It wants to run this way. But let's say you want some reason to push it this direction because you want to collect products over here. So the reverse reaction is spontaneous under standard state conditions. What conditions is going to make this guy negative? How in the world can we make a reaction run spontaneously this way? Well, we have to start messing with the reactants and products. So what conditions is going to make delta G negative? In other words, the reaction to become spontaneous? Well, what must this be? If this is positive and I want this to be negative, this better be negative. And it'd be better, more negative than this is. How do we make this negative? Well, we can't change that. We can't change that to make it negative because these are kelvins and that can't make it negative. This part I can make negative. How do I make that part negative? By having a Q less than 1. The natural log of a fraction is negative. So that's how I make this term negative. All right, so that is how I do that. Well, how do I make this fraction less than 1? By having a bunch of reactants. So if I get the denominator big, the numerator small, Q is going to be a tiny enough fraction, and this enough negative to turn this term into big enough negative to force this reaction to be spontaneous. So if Q is less than 1, that's what we said, if Q is less than 1, this term becomes negative. Q is less than 1 when reactants are big. So eventually you can dump enough reactant in. You push in a bunch of reactants. Chatelier's principle says you could force it this way. You can turn a reaction that would be spontaneous this way and force it to go in that direction by manipulating the amount of reactants and products. Okay, so I am not doing any calculations per se here, but you will have an opportunity to put in values and determine delta G that's not standard when you know the standard value, or you can determine the value of Q needed in order to turn it spontaneous. So you might do calculations with it. For the most part, it's plug and chug, but watch your units.